One of the things that we often want to do is look not just at individual values, but rather graphical representations of those values. And we're going to see why that is in a second. So let's take a new data set here. You might recall that last week we looked at this New York City flights data set, which essentially contains all records of domestic flights that flew into New York, that flew out, was it into or out of? I think I've made a mistake there. I think that should say out of. Yes, I should have said out of. Right, that flew out of New York City in 2013. And so I've just read in the data set, which is this New York flights data set. And you can see that the data set, let me make this a bit bigger so it doesn't overlap. The data set contains, date information, year, month, day. It contains departure times, arrival times, the carrier, so which airline was flying it, the flight number, the origin, which is the airport in New York. So you have Newark, LaGuardia, and JFK, for those of you who have been to New York. And the destination of the flight is the location where it's obviously intended to fly to. And then there's sort of flight time details and things like that. Now, the reason why graphical representations of data are frequently useful to look at is essentially because when we look at absolute frequencies or even relative frequencies, with many different categories of data, it can very rapidly become inefficient to just look at numbers. So you can look at absolute frequencies, and that can definitely be interesting. So let's do, for example, the absolute frequency of the number of flights per month into New York. And what you can see is that on average, there's around 27, 28, 29,000 flights that fly into New York, that fly out of New York every year, or every month, sorry. But if we don't want to look at absolute numbers, we instead want to know, for example, what is the fraction of flights according to each airline? Then we can look at the relative frequencies of each carrier. So we can do our table of the number of the carrier entries, of the carrier observations per of our data set. We can divide by the number of observations to get relative frequency. And that gives us these numbers here. And these are in scientific notation. They're a little bit hard to look at. So instead, we can reformat this just as a percentage of flights. So we can just do the multiplication of the fraction by 100 to get percentages, and then round it to 2 decimal places, because that's all we really care about. And we can then get this data set. So this is essentially the percentage of flights that flew out of New York as a function of the different carriers in 2013. And you can see that there are a couple of standouts. So these three here in particular, right? And this one here, where you have more than 15%. And just so that if you want to convert these code names into the actual airlines, that's what these are here. So you can see that the most common ones here, which are UA, B6 and EV, those are respectively United Airlines, as you might expect. B6 is JetBlue and EV is ExpressJet, so 2 budget airlines. So we can still digest this information. This is still not too many categories for us to be able to understand. But this can very quickly run out of steam. So for example, if we wanted to look at the absolute number of flights that flew out of each airport, you can see they're actually pretty evenly spread between the 3 airports. But if you wanted to do that for destination, then things obviously get a little bit out of hand, right? So it's quite hard to digest information from all of these different values, right? As humans, we're not very good at it. And so for this purpose, we usually look at graphical representations of data. Okay, so as a first example of a graphical representation, we're going to take that same histogram, that frequency of flights by carrier, and we're going to create a bar chart. So a bar chart's a very, very simple means of looking at the frequency histogram of the frequency of categorical data, of here qualitative data. And you can see that obviously there are these 4 standouts that we saw. These are the 4 airlines that had the most flights. And Again, we can demonstrate that this is qualitative because if I reorder the x-axis here, nothing changes, right? And my ability to interpret these data don't change if I shuffle the x-axis. Okay, so these are qualitative data. The bar chart is really useful when you have these sorts of qualitative variables where you want to know the frequencies and relative frequencies of, but it becomes pretty unwieldy if you start to have larger numbers of categories. So for example, here we've taken this destinations that we had, and we said we wanted to look at the destinations in the number of flights to each destination. And you've seen that actually we can't interpret this really at all because the vast majority of the destinations have been hidden because the labels have overlapped. And so the way in which it's been plotted has been removed. We can make this a little bit easier to interpret if instead of saying I want to plot all destinations, you say I just want to plot the 15 most common destinations. And then all of a sudden the bar chart becomes useful again. Okay, so we can see that the most common destinations here are LAX, so Los Angeles, Atlanta, and ORD is Chicago, Chicago O'Hare Airport. So these three are the most common destinations for flights out of New York. And so this is just an example of how you can use this graphical representation in order to understand the data set for qualitative data. If we don't have qualitative data, or rather we don't have data that sits on a nominal or ordinal scale, if instead we have continuous scale data, using the bar chart becomes kind of less useful. And the reason for that is because when we have continuous scale data, the X value means something, and the differences between the X value means something. So for example, if we go back to our coin tossing data set and we plot the bar chart of the outcomes of our coin tosses, then we see, okay, this is probably not a very good coin because it seems to be reproducing, fewer heads overall than you might expect from random chance. But more importantly, there's this gap here, or rather the lack of a gap here, where we have the difference between 4 heads thrown and 6 heads thrown has been smashed together. Because again, in this bar chart, there's no quantification of the meaningful difference between the X values. They are assumed to be meaningless. And so instead of showing this stuff as a bar chart, we then want to instead use something where we retain the information. We retain the information that's present in the x-axis, and that is the histogram. So essentially what we want to do is we want to count frequencies that fall within a certain interval. So again, if I go down here, I want to look at the number of observations that fall within the interval 0.7 to 1.25, 1.75 to 1.2 to 2.25, etc., etc., etc. And what you see when you make those observations is this: you have, 11 objects at unity, you have 9 at 2, 7 at 3, etc., etc. And now we have a meaningful gap at 5 where we didn't make any observations. We've also got meaningful gaps between the values, right? And that's because the intervals that we requested included gaps where, by definition, there can't be any observations here because these are discrete values. These are discrete numbers that fall on the integers, right? And so these are 0 by definition, okay? These gaps in between. And that's interesting because it tells you something about the histogram. And that is that for equally spaced data, the area of the bar in the histogram is related or proportional to the relative frequency of the observations. And that's really important for how we as humans interpret these data. And we'll see more about that in a second. So here we've got this coin tossing data set where we have discrete data, but there is absolutely no reason that our histogram binning need be restricted to discrete data. So I can take 2 data sets or 2 sets of observations for one data set, which here I've constructed as being the number of mice in Disney films, which is a discrete value because it's an integer, versus the height of the mice in Disney films, which is continuous because it's a measurement of height, and constructed 2 histograms. And you can see that in the frequency space of per film, then there are an overdensity or an increase in the number of films that have 2 mice in them in Disney, but generally there's sort of 0 or more. Whereas if you look at the heights, there's a distinct population of mice that have heights that is less than 10 centimeters, which is sort of what I would say is arguably normal for a mouse. And then you have these two freakish outliers of Mickey and Minnie, who are both over 65 centimeters tall. So this is a good example of how you can generalize the histogram to both discrete and continuous data. But this lies an important caveat about the histogram. As I said, the bin width has meaning because the data scale, even if you have discrete, the data scale is continuous. And if you have equal bin sizes, so you don't have variable bin sizes, and you're plotting absolute or relative frequency. So let me put this another way. The area of the bins is proportional to the relative frequency unless you have both variable bin sizes, so I don't use equal binning in my x-axis, and I plot absolute frequency. If these two are satisfied, if you have variable bin sizes and you're plotting absolute frequency, the area of the bars in a histogram no longer is proportional to relative frequency. And we'll see why that is very, very dangerous in a few seconds. So what that means is that I can take this exact same data set. Notice there's a strong peak at 2 in the number of mice per Disney film, and there's a strong population that peaks around 7 centimeters in height in the height, but that these two Minnie and Mickeys are very, very much outliers. They're very unusual and they don't represent the normal distribution of data. If I take variable bin sizes and absolute frequency, I can construct two histograms that show almost the exact opposite visual trends as was shown in the above case. So I can show visually, it looks like there are many, many more observations of small numbers than large numbers in the number of mice. So it's a monotonically decreasing trend. And here it looks like you have a strong bimodality in the population and that there's lots and lots of things with Minnie and Mickey sized mice in them, right? And this is just due to the way in which the human eye interprets area in the histogram as being meaningful. And so in fact, if you try and do this in R and display data this way in R, you actually get a warning that says you shouldn't be doing this. You may well see the same behavior in Python. However, if you plot relative frequencies, or rather densities, on the x-axis, or you have equidistant bins, you can't create this problem. So here's the example of me showing non-equal bins, but now with fractional density or relative quantity on the y-axis. And all of a sudden we get back to the same sorts of display where you have a strong peak at 2, or, at around the normal, the number of mice in the mean of the population. So we have a strong peak around here, right? And less data on either side. And here again, we have a strong peak around 7. And, obviously Minnie and Mickey go back to being outliers in the distribution. And so this is an important caveat, an important thing for you to understand about how we interpret and how we read histograms. The next thing that you can look at is what's called the kernel density estimate. And that's essentially because the way in which we construct histograms artificially categorizes data. Okay, we make a decision where I want these bins to fall. So we have made an artificial choice about how I want to combine data together. One way around that artificial choice is what's called the kernel density estimate. And you can roughly think of a kernel density estimate in the simplest sense as being a sliding histogram, a histogram where the window that you are using to construct your histogram drags along the x-axis, and the value at every point is essentially the number of things that fall within that window. Mathematically, it's determined like this. And actually, if you construct the kernel density in a step-by-step fashion, which is what I'm showing with this animation here, then what you end up with is something that that sort of builds up over time. So I've got 400 observations of data that I'm fitting with a Gaussian kernel. So this kernel here, this K here, is the kernel that I use to make my kernel density. And what this kernel density is it's essentially just the summation of the kernel located at each point X of the data, right? Centered on each point X of the data with some width, what we call the bandwidth H, and then normalized so that it integrates to unity. So what you can see is I'm adding in data, and I basically take the kernel, which is this Gaussian you can see in the dotted line at the bottom, and I just add one of those onto the total every time. And that's what you can see is the difference between the black and the red. And so I'm building up, I'm doing this addition, I'm building up over time and building and building and building and building until I get to the end result, which is this red line here. This is my final kernel density estimate of my distribution of data, 400 data points, which I computed, which I just constructed, which the distribution of which is not, the true distribution of which is shown as this green line. So you can see the equivalent as a histogram as well, which is shown as the blue. So this is the artificial histogram binning. And then lastly, in the dashed line, you can see the kernel density estimate using a rectangular kernel, not using a Gaussian kernel. So that rectangular kernel has the same width as the bins of my histogram. So I've used the same width as my histogram binning for the rectangular kernel. But essentially what's happening is it's dragging that rectangular kernel continuously across the x-axis and giving me the number of observations that fall within that rectangular kernel instantaneously at every element. And so there is no discretization of the data in the kernel density estimate. And that's the main utility of the kernel density estimate. Another thing that we can do to quantify the different sort of distribution of data that we have in a particular variable is we can look at what's called the empirical cumulative distribution function, the ECDF. So let's start with some discrete data. We're starting with our coin toss data set again. So here we have a coin that we just found on the ground. We don't know whether it's a fair coin or not. We throw it 6 times and we count the number of heads that we get in a row. And then we do that again and again and again and again. And we see that the coin gives 1 head most frequently, and then 2, and then 3, and then 4, and then 6. Now, if instead of looking this in terms of the frequency, just the frequency of each value, I instead look at the cumulative version of this frequency, I get this. So I basically take the cumulative sum of this distribution along the x-axis. And so when I hit 1, all of a sudden I go from no observations to 11. If I then step into this gap, obviously I don't add anything. So the value stays the same. I then add another 9, and then I hit the gap, and then I add another 7, etc., until I get to 6, where I add the last data point here. So this is the cumulative distribution of that frequency histogram. And the ECDF is essentially something quite analogous to this step function that we've just created here. So it's the same sort of thing, except it's normalized such that it shows the relative fraction of data. So the relative frequency of data, cumulative frequency of data up to that point X, up till the point on the x-axis X. So again, we calculate the ECDF of this coin toss data set. We have 40% of the data are observed at a value of 1, or rather are observed at a value less than 2. If we then go to a value between 2 and 3, we have 65%, 70%, etc. And we go da, 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 da. So this is the empirical cumulative distribution function. Similar to like we saw with the histogram, we can generalize the empirical cumulative distribution function to continuous data, because it basically just does exactly the same computation, but for the continuous data set that we have. And so you can take, for example, a continuous distribution of data, which I've shown here using the kernel density estimate of a bunch of randomly distributed data. So here what I've done is I've used the random normal function in R to generate 10,000 random normally distributed data points. And then I've used magplot to plot the kernel density estimate, which is used just using this thing called density. And then I've labeled my axes, as you always should. And what you can see is that you have the KDE here, and for some reason the plot hasn't shown up. So what I'm going to do is I'm going to go over to my little console here, and I'm going to do this live. Rnorm 40. So I've just created the same data set. I've now plotted the density of that data set here. And now what I'm going to do is I'm going to plot the ECDF of that data set. And this is what the ECDF of that data set looks like. Okay, so again, it looks more continuous now, and it basically describes the fraction of data that fall up to the value on the x-axis. So here you can see the peak of this distribution is around 0. And indeed, if you go to 0, you have 50% odd of the data set falls less than 0. Okay. One important thing to note